I'm Georg. Greetings from Vienna. At Magenta, we're a telecommunication carrier, and we have a nice joke going. We're usually selling telecommunications. So you would assume that we are really good at communicating as humans with each other. But the joke goes, we are really bad as humans in the enterprise communicating with each other. And this is actually a problem because nowadays management asks for AI grade data. And the traditional systems don't cut it. I hope that after this talk, you will understand what we changed to make this work. And the short answer is we changed the data structure of how we operate with data pipelines at scale. So who am I? I'm at Magenta called a senior data expert. I also work in research institutions. I'm frequently organizing meetups in my local community about data, science, and engineering. And if you want to connect, you will find the details here and in my blog and so on. So let's dive right in. There is a lot of chaos out there. Our network hopefully doesn't look like this, but there are telco networks in Asia. And I would really not want to be the technician that has to debug this. But it tends that non-physical things are usually structured like this. Another question is, why is this the case and how can we fix it? In our case, I know the story, and it's basically time. At the specific point in time, the tools that were chosen, things were right. But when everything changed, there was a merger, the demand for data grows over time. And basically, in the outside world, methodology and tooling changes, but the enterprise stays put. And eventually, technology is lacking. We're in particular missing lineage, semantics, collaboration between humans and machines. And the problem is that manifesting as high lead times and limited quality of the data, not AI-grade quality. And that is a problem because everyone agrees that the best thing that you can do to make your AI great is to feed it the right high-quality data. So how is the situation looking at our case? I'm short-circuiting things here a little bit, so there's a lot of things on this slide. But if we start on the left-hand side, initially, basically, there was a little bit of data and people were storing this and producing dashboards. And over time, more and more people and departments were added and the chaos was growing. Literally, Excel was the only constant. And that's pretty much the short version. How are we going to change this? Well, first and foremost, it's about finding right accountability to people by defining explicit data dependencies and reducing the silos around humans and machines by defining our own domain-specific languages and by changing task-based, not connected scalar data processing steps where the data dependencies are a problem or maybe the enemy into a new data structure, a graph, like a social network. And this graph means the computer can reason about things and can help us tackle the tricky data challenges. So let's dive right in. What is the difference between asset or graph-based and task-based orchestration? Everyone likes chocolate cookies and Christmas time is coming up. So, well, how do we bake chocolate cookies? We take eggs and some other things like flour, and we want to produce the thing that we care about with chocolate cookies. But we have tasks and states. So if you think in the traditional way of thinking, it is tasks, and we would combine the items and then produce the dough. Not yet with chocolate. We can add the chocolate, and then we have the chocolate cookie dough, and then we bake it in the oven. So we have a result. Let's put these things aside and make it a bit more clear by connecting the individual boxes. And we already see how tasks describe not really what we care about, rather the states. So let's make this more clear. How do things look like? And when we juxtapose it next to each other. The top, more bluish, shows how Airflow and traditional task-based orchestration tools display the data pipeline. The bottom one is a graph-based data pipeline, and this has tremendous benefits. Not only do humans and machines understand far better how things are connected, but there are a couple of advantages that can be reaped by traversing or turning to this new graph-based representation. The first and foremost is its quality. We can add a quality check to the individual asset that we care about. If it's a table, a view in a database, or a machine learning model, we can add it right where we need it. We can stop the processing of a subgraph or just let it run through and emit a warning if that is needed. In the traditional world, this was really, really hard because we were triggering the whole graph all the time. So this, let's call it hexagonal reasoning, was pretty much impossible and very error-prone and very manual. The same is true for asset freshness. So we can attach questions or tags, or let's say freshness tests, to these individual things that we care about, compared to the traditional way of operating, where basically the whole graph of an enterprise data warehouse was scheduled. And this is really critical when we think about real time, not so much like the talk before with maybe milliseconds of latency, but even if it's maybe 5 minutes of latency, it could save a lot for your credit card if you just trigger a particular subgraph of your data warehouse that really needs this high refresh rate. And last but not least, this graph allows us to work in a different way with the pipelines. Traditionally, you would define jobs of step 1, 2, 3 that follow one after the other. And this is okay for a couple of jobs and pipelines. But if you're an enterprise and you have hundreds of thousands of interconnected jobs, things get really, really tricky. And the good thing is, instead of having this grow larger than the mind of a human, we can change the data structure to the graph. And now basically the computer, like a calculator for crunching numbers and multiplying matrices, has a data structure to reason about our data dependencies. So instead of manually defining these jobs, we can just tell the computer, this particular asset should refresh on a specific cadence. And everything in between, please update it. And this is really relieving. So how does this work from a technical perspective? This was a lot of high-level motivational concepts. Let's take one step deeper. We have a core data platform, and this core data platform has common components, right? Data and some visualizations. We have various systems that you want to connect to, and that's pretty much it. The interesting difference is how this is set up. Yes, we have an ingestion component, we have some kind of transformation, and we have some orchestration component. But think about a car dealer selling you a Ferrari car. The dealer will maybe tell you the engine is the greatest thing, and you should buy this car for the sole purpose of the engine. Remember, the old days of Oracle, we were buying the best thing that we could buy, but it was not even possible with the best engine to get data into the platform, let alone do AI with that great engine. And this caused a lot of problems down the road, because it was not a full solution that allows you to go from A to B, not a full car, just the engine. And by changing this thinking model about the engine, the data transformation engine, to the overall glue that is keeping things together, the orchestration machinery, we can change the whole way how we view the problems and get a lot of flexibility. Here we're using Dagster for this. For the data transformation, you're using dbt that is tightly integrated into this graph of Dagster. And for ingestion, we use a homegrown framework around Spark and DLT. What means tool silos? Well, at the top, we see the picture that we have established. This is our way of working. We call it data domain or graphy way of working. But traditionally, you have a developer that wants to implement a feature or a fix. And in a larger organization, that might involve multiple teams with different tool stacks to get something done. So for ingestion, you might have one of these tools here going. And then for transformation, you might have something else going on. And then we have the visualization layer. And this is many different teams that are happening that have to be coordinated. And that can be really, really challenging. In our case, this is different. We are collecting machine-readable metadata from the various systems, and then we can bring them directly into the graph, which is sort of a short explanation. What does this mean? The metadata is driving this creation of a graph, and we have a domain-specific language, and we will later see how this works. But this means a developer that should develop something from start to finish has one holistic solution to work with. So in our case, the orchestrator is driving this. On top of this, we have some machinery for ingestion that is Spark in our case, or dbt as a SQL automation tool on top of some database that we have. And then we have some visualization tool. In our case, it's Tableau. So how does a pipeline like this look like? Well, from start to finish, for a mini example, it might look like this. And this is the view of a platform team over automation. This is this asset-based graph, but new concepts we get from this is not only the graph notation, but this metadata-driven pipeline creation, reusable components, and more around CI/CD and branched stateful environments for developing quicker. But I already was teasing the notion of machine-readable metadata. How does this work? Let's look at this example picture here. This is our pipeline testing or sample project, how we like to call it. It has around 50 assets to just test the development of a dummy pipeline for our enterprise solution. The interesting thing is not the quantity of the assets, but that none of these assets was created by a human from the data platform team. It was generated by machine-readable metadata by these, let's call it executable specifications, and then imported into the graph. And this is really powerful because it allows us to scale to many humans collaborating. So from a technical perspective, we have some pseudocode going with for loop that is collecting the metadata and then adding items into the graph. If we look at the individual steps of this graph, let's say ingestion, we would read our ingest definitions. This is a folder of YAML files, and then add these into the graph and then tell Spark what Spark should copy from A to B. The same goes for dbt. In the case of dbt, luckily, we can read this JSON manifest of dbt and then really get already a graph, and we can add it into our orchestration graph, including data quality checks. And I think even more interesting is a homegrown Tableau integration, which, by the way, is open source. So we are connecting to the REST API of Tableau, and unlike the old times, where the whole Tableau server sort of triggering a refresh at 11 in the morning, and maybe the data is of high quality, or maybe not, or maybe it's delayed. In our case now, the Tableau server is refreshed whenever the upstream input changes. So not only do we guarantee high quality data by this, but we also can dramatically increase the refresh rate, but by conserving cloud spend. But things get even more interesting when we look one layer deeper. We now talk about reusable components. Let's dive directly into the code. I don't know who in this round is familiar with something like dependency injection. Usually Java developers are this. But if you think about this function signature and assume you could, as a data scientist, simply specify, I want to receive my customers. I want to receive my products and sales transactions. And I say, I want to have it as a pandas data frame, or perhaps Polars or Spark data frame, but I don't have to care where things are coming from. Then the business logic gets a lot more interesting, a lot more easy, and we get a couple of things from this. We get a decoupled execution model where the platform team might take care of I/O components, which can be really tricky to get right, but someone else with a less technical mindset can perhaps even vibe code the business logic. But on top of this, we can change the I/O components, and we can reduce a very expensive and distributed data pipeline to maybe a developer's notebook. So this can enable swift debugging, but also day one productivity, because in an enterprise, requesting all the necessary permissions can take a lot of time, and also increase all of the self-service. So people that are from the business units that have learned a little bit of Python can actually be embraced by this data platform, and that can be a really powerful thing to have. What is a way to scale this? So now we understand we have a graph, the computer can help us, we have a machine-readable metadata, but how do we really scale this? For large data sets and to a large organization. And this is where the bounded context plays a role. So the thing that we named data domain is something like an atom. We have many of them, and this is sort of the smallest unit of data processing. The individual pieces are the electrons and so on that we discussed so far. The process itself is very straightforward for one of these data atoms or domains, like we call them. Ingest, transform, do something with the data, maybe even visualize it. And what we do is we want to provide better value to the business, but we have to do this in a scalable way, not just for a single sales unit or maybe with a single data team, but in a way that many people can collaborate. Let's see how this scales. We add another team. Well, possibly we could add another data team, but this will not work, right? What do we do instead? Making the data team bigger, well, we have less silos to deal with, but it's still not ideal. Instead, giving them the individual projects would guarantee autonomy, but also chaos. So what can we do instead? We divide people in actually people using the platform or the framework, like we used to call it, and people that are maintaining the platform. And we have a platform team that is basically maintaining the platform and delivering something we call blueprint or template project. And this is literally a blueprint that allows others to instantiate a version of the platform on their own. But because it has the graph, and we call it hexagonal cohesive components around logging, IAM, and so on, but especially because of the graph, things are still tightly connected. So whenever one business unit in their own compartment provides a data set that is perhaps published due to some data governance, data product, metadata, someone else is perhaps consuming it, and via the graph, you can, via an event-based way, trigger the refreshes. And this is then all layered around the building blocks of the infrastructure in deep down with dbt, DAX for orchestration, and then containerized via Docker. Pixie is, I guess, less well known. Most people in the Python ecosystem use UV. However, Pixie is combining the power of pip and UV with Conda. And when you want to work with machine learning or computer vision or robotics, this can be a really must-have thing to have. Around this, we have introduced a lot of new processes around data modeling and basically taking that metadata and automating code from there. What are some takeaways? Well, this integrated asset graph is really key for us to achieve swift development of value for our business, from ingest to transformation and to reporting and data quality, but also for AI. And this is where things get even interesting, especially from a European perspective and sovereignty. We already have this graph from an AI Act reporting perspective, perfect, but even better, when people work with traditional machine learning, we can directly inference these models in line with the graph, just as one more transformation. And even if it's GenAI for SLM, so small language models, also these can just happen directly natively in the graph with perhaps a model running on Ray on Kubernetes. With event-driven connections, the glue that is along the edges of the graph, connecting the individual data assets and guaranteeing better collaboration and scaling. This can enable also retargeting of execution environments in advanced cases. Perhaps instead of paying 50% markup for Databricks, you could retarget to EMR. And this would be happening fully transparent behind the scenes for the users of a platform. What is important for us is that we can enable software engineering principles that in the end drive self-service for the business around the blueprint, around automation and CI/CD, and basically these tested components that allow for dependency injection and basically the business focusing on the business logic only. But what is really driving and gluing everything together is the executable specification, the metadata and the contracts. We use this for interface management and to preserve semantics and basically compliance. And this is the key thing that is allowing us to scale, because we can now have a domain-specific language, let's say a YAML file that is accessible for less technical people and can drive specific nodes and operations in the graph. It's basically just building the processes in a way that makes us very efficient and powerful when working with data. But this is not just something to hear me talk. You can explore this for yourself. So we have published a couple of open source projects. One is the thing that we call local data stack, and it is allowing you to spin up an instance of what I have talked about here today within minutes. It is not as enterprisey, it doesn't have all the bells and whistles, but the core components are there. Enjoy that. And whatever we are doing, for example, with Tableau integration is also an open source contribution from our side, and there's more. So we are contributing a couple of videos and also more components. So for example, the Duck Lake integration, the vertex A integration, and more. All in all, this is a teamwork, and I want to thank the whole team for this. And I have also one last thing to share. This is a new project that I'm exploring and maybe of interest to some people about ranking the data engines. Engine rankings can be always biased when vendors produce it, but here by exploring the notion of football teams and ELO rankings, by relatively ranking the individual plays, maybe it can help identify the right tool that you want to orchestrate via such a graphy approach when you want to really transform data at scale efficiently. With that being said, thank you for this audience.